What's up, people? It's Dan from sagemathtutoring.com, and I have a student who has a statistics test coming up, and here are some problems from the review sheet for that test, and I'm hoping that this will be helpful for not only my student, but some of y'all out there who are taking statistics. So anyway, there are 12 total questions, and we're going to start with this one. In a survey, 169 respondents I believe this is say that they never use a credit card. 1227 say that they use it sometimes, and 2834 say that they use it frequently. What's the probability that a randomly selected person uses credit card frequently? So it's important to remember that probability at its most basic level is the desired outcome over the possible outcome. So I often find it helpful to start actually with the possible outcomes. So let's get clear on that. The possible outcomes in this case are literally all of the different respondents. So it's going to be 169 plus 1227 plus 2834. And that is 4230. So I'm going to write that down. And that again covers what's the possible outcomes. It could have been any of these respondents, but what we're specifically analyzing is the probability that a randomly selected person uses the credit card frequently. So that is this 2834 number right here. So we're going to put that over the 4230, and that is going to reduce to, let's see, approximately 0.67. So we could even use these squiggly lines for approximately. So that's how you do that one. It's often the case that many tests will want the answer rounded off to the nearest hundredth, which is what we did right here. All right, next problem. Let's see, a three-sided die is rolled 2 times. What is the sample space? In other words, list all the possible outcomes. Right, so basically sample space, they kind of sum it up here. It's all the possible outcomes, and the way that you're going to want to kind of tackle this one is just remind yourself it's a three-sided die, so that means that you're either going to get the number 1 showing up, 2 showing up, or 3 showing up, but we're rolling it 2 times, right? So one possible outcome is 1, and then you get 1 again. Another one is 1 and then 2, and then another one is 1 and then 3. And you can kind of go about it in this systematic way. So now we'll analyze. You could get 2 on the first roll, 1 on the second roll. You could get 2 on the first roll, 2 on the second roll, and 2 on the first roll, and 3 on the second roll. And of course, you could keep going with this pattern here. And this gives you the sample space. This is literally all the possible outcomes of 2 rolls that you could get. So that satisfies part A. So I'll just write A right here. Looking at part B, what's the probability that the same number is rolled twice? Okay, so that's when it's helpful to use the sample space. In fact, they're kind of asking what's the sample space first for a reason. Part of the reason has to do with the fact that they know that that's going to make the rest of the problem easier. So what is the probability that the same number is rolled twice? Well, we have this moment right here. We've got this moment, and we've got this moment. So that is 3 desired outcomes over how many possible outcomes? Well, that would be 1, 2, 3, 4, 5, 6, 7, 8, 9 outcomes. So that is 3 over 6, also known as 1/3. So that satisfies part B. B is 1/3. C, what's the probability of rolling at least 1, 2? Okay, so at least 1, 2. Well, let's see. Again, we could rely heavily on the sample space that we just created. And here's at least 1, 2. These all have at least 1, 2. And this one has at least 1, 2. So that is 5 total desired outcomes there over the 9 possible outcomes. All right. So that is how you tackle this one. All right, Amara's poll survey showed that 47% of the respondents chose whatever as the most annoying phrase used in conversation. What's the probability of randomly selecting someone choosing something different from whatever as the most annoying phrase in conversation? All right, so that is basically testing your ability to understand what a compliment is. And by that, I mean a compliment in the statistical sense, where basically, you know, imagine here is all the possible outcomes that you could conceive of as far as, you know, what people consider to be the most annoying phrase in conversation. And so far, what we're learning is that 47% of people think that whatever is the most annoying phrase in conversation. So what's the probability of randomly selecting someone choosing something different from whatever? Well, that would be all of these people, right? And what is that? Well, that would be 53%. Now, I'm using this sort of pie chart thing to kind of give you a good visual of what the heck is going on in this problem. However, if you're going to want to use math in order to find the complement of a percentage, you just take 1 minus, we could say 47%. Now, typically, we're going to want to convert that 47% into a decimal when we make that calculation. So, in other words, if you want to find out how many people don't think that whatever is the most annoying phrase used in conversation, well, it's going to be 1, which is a 100% chance, minus the 47% chance right here. And if you were to do that, you would indeed get 0.53 for that. That's the answer. All right. Among respondents asked which is their favorite seat on a plane, 492 chose the window seat, 8 chose the middle seat, and 306 chose the aisle seat. Okay, if 2 of the surveyed people are randomly selected without replacement, what's the probability that neither of them chose the middle seat? Right, so one thing we could do here is we could first get clear on how many people there are. So it's going to be 492 plus 8, which is going to be 500, plus 306. That's going to be 806. So basically there's 806 possibilities. And so that's going to be the denominator, because again, probability is desired outcome over possible outcome. So the 806 is going to be in the denominator. So if 2 of the surveyed people are randomly selected without replacement, what's the probability that neither of them chose the middle seat? So let's say that this is the first person chosen. So I'll call it first person. Well, the chances of this person being a person who did not choose the middle seat is going to be 492 plus 306. So that's going to be 798. Right? Because the 8 number right here represents all the people who did choose the middle seat. We're looking for people who did not choose the middle seat. So that would be 492, namely the people who chose the window seat, plus 306, namely the people who chose the aisle seat. So that is the first person chosen. The chances of the first person being chosen being somebody who did not choose the middle seat is going to be 798 over 806. So once you've chosen that person, there are now not 806 possibilities, but 805 possibilities. Now, why am I saying that? The reason I'm saying that is because the 2 people are randomly selected without replacement. So that means the second person chosen, the possible outcomes are only 805 because this first person was already chosen. All right, so 805 possibilities at this point. And we're going to imagine that this second person right here, which I'll label, this is the second person that we're choosing. We're going to sort of wrap on the fact that we already, did this calculation. These are all the people who didn't choose the middle seat. So we're still going to pull from this kind of pool. However, one of these people was already chosen the first time around. So this is going to be 7, we'll keep it black, 797. And in order to find the probability of the first person being chosen and then the second person being chosen, well, we're definitely going to have to multiply these guys together. And that will definitely equal, well, once again, I should really say this would be approximately 0.98. All right. So that is the chances of the first person being chosen being somebody who's not choosing the middle seat, and then we choose another person, and that person also doesn't choose or prefer the middle seat, right? So that's going to be 0.98. Now, let's get clear about this situation. These are not independent events. Independent events are such that something happens and then the next thing happens, and the probability of the next thing, like this drawing of the second person, isn't affected by what happened before. That would be independent. Now, this is not independent. This is a dependent scenario where the probability of the second person kind of depends on what happened before. So that's just something to take into account. All right. So looking at this next part, if 20 different people are randomly selected without replacement, what's the probability that none of them chose the middle seat? Right. So basically, this is sort of setting us up to do like a huge, crazy calculation where it's like, um, 798 over 806. That's the first person, and then it's going to be like 797 over 805, and then after that it's going to be like 796 over 804. And that would just keep going until we have like 20 total people taken into account. Now, that is a crazy calculation that no one wants to friggin' deal with, all right? So the good news is, when it comes to statistics people, they decided, well, it was proven, we could say, that you don't have to do all of that. Now, if you were going to be treating each of these events as dependent, then you would kind of have to do this. But what they realized, or what they decided, or what they proved, is that as long as this number, 20, is less than 5% of the total amount of people, which by the way is 806, as long as this 20 person sample is less than 5% of 806, then you're officially allowed to treat each drawing as an independent event. Now, that might seem like, okay, what's the big deal about that? How does that make things easier for us? Well, actually, it makes things a lot easier for us. I'm going to explain why. All right? And, well, here's why. The reason why it's easier is because if you treat each of these as an independent event, then you could just be like 798 times 806 times another 798 times 806. And you would just do this 20 times. All right. Now, you might be asking, okay, well, how is that making it easier? I still have to write it out friggin' 20 times. Well, actually, you don't. Because the truth of the matter is, what this really equals is this. 798 to the 20th power, right? Because it's going to be 798 times itself 20 times, also known as 798 raised to the 20th power, all over 806 raised to the 20th power. Now, this is something that you can totally plug into your calculator. And in fact, I'm going to do it right now. I'm going to tell you what it is. So this right here, kind of running out of room here, but we'll bring it all the way up here. This right here is approximately equal to 0.82. All right. So why was I able to treat each of these like they were independent? Well, I was able to because 20 is certainly less than 5% of the total amount of people in the population that we're analyzing. All right. Now, some of you might be asking, well, how did I know that? How did I know that, what is it, 20 is less than 5%? Well, one thing you could do is you could get clear on, okay, well, what is 5% of 806? And I'll just do that right now. We'll do it right here. So 5% of 806 is really 0.05 times 806, and that would be 40.3. And so that's 5% of 806, and clearly 20 is less than 40.3. So that's why we're allowed to use this rule. Moving on. All right, the chart below, there's my thumb. The chart below contains enrollment in thousands of burglary data. Find the best predicted number of burglaries for Ohio State, which has an enrollment of 51,800 students. In thousands, this would be 51.8. So we want to kind of remember that. This is all in thousands. So what that means is this is like not 36, but actually 36,000 and so on. What's the regression equation? See output below. So they're asking all these questions about like a regression equation, predicted number, see output below. So what this makes me realize is that they're kind of giving us all the information down here. This is information that you could definitely get by using your calculator if you have like a TI-84, which if you're taking statistics, you probably do. Your teacher probably went over how to, plug in these kinds of numbers and getting your regression equation and all that, and you would actually get something like this on your calculator screen. So anyway, what's the regression equation? Well, that would be, let's see, that actually has a lot to do with this. So we have the intercept and the slope. I like to think of the regression equation as akin to like a line in slope-intercept form, where it's like, here's your dependent variable and your output. This right here is your slope, and this right here is your y-intercept. We'll just call that the output. And this right here is the input. So if you've taken algebra, this should be pretty familiar with you, to you. However, I will say that when you're doing the regression equation, they like to kind of flip things around where it's like they actually write the y-intercept first, and then they write this slope term over here. All right, so I think as long as you're sort of aware that this is very much like the slope-intercept form of a line. Now look at this, they give you the intercept. So basically, the equation would be as follows. Y, sometimes they put this symbol above it, equals, and in this case, it would be the intercept first. Now, they give you the intercept, it's right here. We're going to round that off to negative 36.8. And it's going to be plus the slope, which is such that we're going to round it to, we'll round it to 3.47. Times x. So you could use the intercept and the slope over here, but you know what? I'm also seeing you could use this right here also, because It looks like the burglaries is the Y in this case, and the enrollment is the X in this case. So you could also rely on this guy right here, and this is multiplication. So it's like 3.46 blah 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 times the enrollment, right? And they're kind of clearing that up too. They're like independent variables enrollment. That means the X variable. Dependent variable is the burglaries, and that means the Y variable. So we definitely did this right. So that's that. Let's see. What is the predicted number of burglaries for Ohio State? We'll label this A. B. Let's see. B says has enrollment of 51,800 students, or 51.8 in thousands. Yeah, so all that is just a matter of using this formula where it's like, same formula, but for X, you're going to plug in that number. And we'll blow this up a little bit. Sorry for the delay. Sometimes it's the program glitches a little bit. So anyway, what do we got? 51.8. So that's going to be the X value that goes right here. So we'll do that right now. 51.8 goes right there. And when I actually do this calculation, what I would get is 143. So that's how you do that one. That's just a matter of relying on the formula that you found in part A. All right, C. Is the predicted number of burglaries close to 329? No. It's 143. Which is the actual value. So that shows that the correlation might not be that strong. That shows that the correlation of like enrollments and burglaries might not be that strong. What is the correlation coefficient? Well, that's the R, which is right here. So that's the correlation coefficient right here. So I'll write that. C. 0.56. We'll just round it to that. And let's see. Does it indicate a strong linear correlation between the two variables? No, it does not. And the reason is because you can think of like 0 being like a really crappy correlation. And from 0, so it's bad. We'll say little correlation. I'm not going to use crappy. Little correlation. From this to 0.6, we could say is a moderate correlation, and from 0.6 to 1, that is a strong correlation. Maybe instead of the word little, I could have used weak, but nonetheless, you get the idea. From 0 to 0.2, weak correlation or little correlation. From 0.2 to 0.6, we have a moderate correlation. And from 0.6 to 1, we have a strong correlation. Clearly, 5.6 is like right around here. And that's, not a strong correlation. And, it's not a weak correlation, but it's not a strong correlation, and that's what they're asking. Does it indicate a strong linear correlation? And the answer is no. All right. The CIA has specialists who analyze the frequencies of letters in the alphabet in an attempt to decipher intercepted messages that are sent as ciphered text. In standard English text, the letter E is used at the rate 12.7%. Keep in mind, this is such that you might want to turn it into a decimal. If it was to be turned into a decimal, that would be 0.127. In fact, I'm going to write that. I'm going to write that right now, just as a nice reminder. All right. So, moving on. Find the mean and the standard deviation for the number of times the letter E will be found on a typical page of 2,600 characters. Right, so this is such that you're going to want to use this formula where it's like the mean, sometimes represented as this mu symbol, equals the number of people or things you're analyzing times the percentage or the probability. That will give you the mean in one of these kinds of problems here. The standard deviation, I'll just get this over with and write that as well. That's going to be the square root of n times p, but we're also going to multiply that times q. And q, in case you're not sure, is the complement of p, also known as 1 minus p. And this is all very abstract, but we're going to bring it down to earth in a moment. So the mean is what we want to find first. So this is the mean. So we know that the mean is going to be n, which is the amount of people or things you're analyzing, times the percentage. So on the next line, I'll just write mu equals empty parentheses. Well, what goes in here? Well, that would be 2,600. Because that's how many, in this case, it would be characters. And the percentage of E showing up is going to be 12.7%, also known as 0.127. So I'll write that here. One, two, seven. All right, so, and when we do that calculation, it becomes, drum roll, 330.2. So that's the mean. All right. Okay, moving on. So we have the standard deviation to contend with now. And that's going to be the square root of n times p. But here's the deal. We already found n times p. So I'm just literally going to write 330.2. And we're going to multiply that times q. I'm going to draw empty parentheses here representing where q is going to go. Now here's q right here. Q is the complement of p, and the complement is always going to be 1 minus p, right? So the complement of p, the complement of 12.7% is going to be 87.3%. So let's see, 87.3%, but that's also known as 0.873. So that's what goes here. And at this point, we're just going to perform all these calculations, right? Now I'm actually going to just do it in my calculator. And what I'm going to get is that the standard deviation is equal to, that'll be approximately at least. So we'll use the approximation symbols. That'd be approximately 17. So that is A, right there. That's part A. B, what's the range of usual values? So usual values are going to be two standard deviations, within two standard deviations of the mean. So we already know that the mean is this, and one standard deviation is 17. So one way of visualizing this one is that you'd have like the mean in the middle. The mean's in the middle. Let me fix that. I made a mistake. Some of you, I'm sure, caught that. 330.2. And then two standard deviations from here. It's like 1, 2. 1, 2. And each of these is 17 units long. All right. And this whole range represents the range of usual values. All right. So the question is, if we want to know what the range of usual values is, we want to know, all right, well, what's this number? And what's this number? Well, clearly this is going to be 330.2 plus 17 plus another 17. You could also think of it as 330.2 plus 34. So that's going to be 364.2 right there. And this will be 330.2 minus 17 minus another 17, also known as 330.2 minus 34. So that would give you 296.2. So the range of usual values is going to be between 296.2 and 364.2. So I'll draw like a gold half rectangle around our answer in that case. So, in an intercepted ciphered message sent to France, a page of 2,600 characters is found to have a letter E occurring 290 times. Is 290 typical, significantly high, or significantly low? Well, seeing as how we just came up with the usual values and the range of usual values, and the lowest value in the range of usual values was 296.2. Well, clearly 290 is even less than that. So that is significantly low. You know, if the lowest number of the range of usual values is 296.2, and this is even less than that, then it's unusually low, also known as significantly low. So that's C. I'm not even going to write that down. Just need you to follow how that works. All right, looking at D, find the probability that a page of 2,600 characters has exactly 330 letter E's. So that is a classic binomial problem that you would have to plug into your TI-84, or you would want to. I mean, there's a way to do it algebraically, but you would want to use your TI-84 for that. And I'll just tell you that you would want to use this binomial, this setting. And what I'm going to do is I'm going to put a link below the video to another video where they teach you how to use the calculator to find something like this. All right, so in the comment section or the description below, I'll mention 6D, and I'll put a link having to do with how to plug these numbers into your calculator. All right, table below shows the drug test results for a set of potential employees. All right, I see positive test results in this column, negative test results in this column. So this is just talking about the test results. The test could be wrong, but this is such that the test tested positive. This is such that the test tested negative. This row represents the fact that the subject actually used drugs, and this row represents the fact that the subject did not use drugs. All right, so find the probability of selecting someone who got a false negative result. So it would be a negative result, but a false negative. So that's this box right here. So for A, seeing as how probability is desired over possible, well, the desired in this case is 6, because that's how many people are in this box. And it's going to be all over the possible outcomes. Well, the possible outcomes has to do with how many people you're even analyzing. 44 plus 6 is 50, plus 90 is 140, plus 860 is 1,000. So it's going to be 6 out of 1,000. You could also convert that to this decimal. That's the answer. All right, if one of the test subjects is randomly selected, find the probability that the subject had a positive test result or a negative test result. Okay, so there is a formula to figure out, what's the chances of one thing happening or another thing happening. I mean, maybe we'll discuss that further in this video. But in a way, this problem is easier than that. And that, if you really think about it, the probability that a subject gets a positive test result or a negative test result, well, here's the column that represents all the positive result people. Here's the column that represents all the negative result people. So the probability of either of these happening is 100%, also known as 1. So I'm just going to write that. Probability, I'll write 100%. 100%, aka 1. And 1 in quotes. This is really converting 100% to a quote-unquote decimal. It would be 1. All right, moving on. Let's see. C. If one of the test subjects is randomly selected, find the probability that a subject had a positive test result or does not use drugs. Okay, so actually this is a good opportunity for us to use the formula that I was kind of talking about before. I'm actually going to write the formula right here. So it's like the probability of A or B, probability of one thing happening or another thing happening. Well, that's going to be equal to the following. That's going to be equal to this. The probability of the first thing happening plus the probability of the second thing happening minus the probability of both of these things happening at the same time. And when I say happening, we will say that A is the event of, let's see, what are they asking about? So, first of all, let me remind myself we're on problem 7C. So looking here, A is the event of the subject having a positive test result. So I'm actually just going to call that pos. And B is the event that we're calling, let's see, does not use drugs. So I'm just going to say no drugs. Okay. So no drugs. And from there, we could just sort of use this table to piece together these probabilities. And we'll start with the probability of A. So when looking at the probability of A, what we have is the probability of getting a positive test result, right? Well, that's going to be this whole column here. So that's going to be 90 plus 44, also known as 134. That's the desired over the possible outcomes of 1,000 people. And now we're going to look at the probability of B. Now, what's B? The event of no drugs, a person not doing drugs. Well, that's this row down here. Subject is not a drug user, so that'd be 90 plus 860. So therefore, the desired in that case, and let's forget or remember to write plus, the desired in that case is going to be 950 over 1,000. And then we're going to be subtracting the probability of A and B happening at the same time. Well, A is a positive test result. B is no drugs. So the intersection of this column and this row is this cell right here, which is 90. So that's going to be 90 as the desired outcome over 1,000. And what we would get as a result of that is approximately, I should probably just remember to do these squiggly lines every single time. That would be 0.994. So that is how you do part C. All right, relying heavily on this formula. Probability of A or B happening, you're going to want to use that formula right there. So let's look at this next one, which is D. If one of the test subjects is randomly selected, find the probability that the subject had a positive test result and uses drugs. Okay, so that is fairly straightforward in that we're looking for the positive test result, so that's this column, and using drugs, so that's this row. So that's going to be 44, because this is the cell that represents the intersection of the subject having a positive test result and using drugs. And that is 44 in that cell. So we're going to write that 44 over 1,000, also known as 0.044. So that is D. All right, looking at E. If one of the test subjects is randomly selected, find the probability that the subject had a positive test result given that the subject uses drugs. Right. So these are problems that require you to use another formula. And that other formula that you're going to want to use for the given problems is this. It's like the probability of A given that B already occurred is going to be the probability of A and B happening all over the probability of B happening. Okay, so this is the special formula when they're using the word like given that, the words given that. So let's look at it down here. Well, actually, let's get clear. Let's have A be the event of subject had a positive test result. That's going to be pos. Positive test result, so that's pos. And B is the given that thing. So it's like given that the subject uses drugs, so it'll be like drugs. All right? So, therefore, the answer to that one, we'll just do all the work over here. The answer to that one is going to be probability of A given B. That's going to equal the probability of A and B. Well, probability of A and B is the intersection between the positive row and the drug user column, or the positive column and the drug user row. So the positive column's right here, and the drug user row is right here. So that's going to be, once again, 44 over 1,000. So you could just write that here. And that's going to be all over the probability of B happening. So the probability of somebody being a drug user, and that's represented entirely by this row, and that's 44 plus 6. So that's going to be 50. So therefore, we're going to write 50 over 1,000. Now, some of you who are decently savvy at doing calculations, you might know that we could sort of drop the 1,000s out of the picture entirely. But regardless, even if you plug this into your calculator, you would end up getting 0.88. So that is the answer to E. Okay, groups of people aged 15 through 65 are randomly selected and arranged in groups of 6, the random variable x is the number in the group who says that their family or partner contribute the most to their happiness. Find the mean and standard deviation. Okay, well, focusing on this part first, it's like find the mean and standard deviation. Well, the mean in this case is expected value. You have, what is this? The number in the group who say their family contribute most of their happiness is 0. So it's like a 0.001% chance that it's 0. There's a 0.003% chance that it's 1. There's a 0.025 chance that it's 2. So you're going to want to use the expected value. So for this, there is a way to calculate it. However, the teacher is typically going to want you to use your calculator for this, believe it or not, especially in the college level. They actually want you to get really good at using that TI-84 calculator. So I'm going to do something similar with regards to this question that I did with a previous question. I believe it was number 6, where I'm going to post a link below referencing how to find the expected value and the standard deviation in for a problem like this using your TI-84. All right, so you could look for the link for that. I will say though, let's look at the rest of the problem. What is the probability that 4 or more people in the group say that their family or partner contribute most of their happiness? All right, so this we can do on our own though, because it's like, what are the chances that 4 or more? So that's, what are the chances that it's one of these? Well, all you have to do is add these probabilities up. You just add 0.279 plus 0.373 plus 0.208. And if you're going to do that, I'll just write it. I'm getting lazy because I'm tired and it's late. But this is what it would be. And if we were to add that, we would get 0.860, also known as just 0.86. So that's the answer to the next part down here. Once again, look for the link for this part. And basically just follow the directions that whatever that other YouTube video says to do for the TI-84. Do the same thing, only plug these numbers into the calculator. That's all. All right, so let's see. A graph below depicts the normal distribution of the temperature for adults. It's normally distributed with a mean of 98.3 and a standard deviation of 0.7. Shade the region of the graph that represents the percent of people with a temperature between 97 and 100. All right, well, let's see. Between 97 and 100, it's fairly straightforward. I mean, 97 would be like right around here, and 100 would be, somewhere here. So we're definitely looking at this region right here, right? So that is part A. Part B, what are the z-scores for 97 and 100? All right, so 97 and 100. So this is the first time in this video where they're asking for z-scores. Now, it definitely is going to be beneficial to remember this, which is z equals x minus whatever the mean is over the standard deviation. So we're just going to literally rely as straightforwardly as possible on this equation. So we'll be like finding the z-score for 97. Well, that's going to be a z sub 97. We'll just label it that way. It's going to be 97 minus the mean. Well, what's the mean? They already told us the mean. The mean is 98.3, right? So it's like 98.3 all over the standard deviation, which is 0.7. And when you work that out, it would be negative 1.86. So that's the z-score for 97. So the z-score for, 100, that's going to be 100 minus 98.3 all over 0.7. And that ends up becoming 2.43. All right, so this is satisfying part B of the problem. Moving on to part C. Convert all the temperatures on the graph below to z-scores. Right, well, if you look at the graph, and I'm going to zoom in a moment. So here are all the values they would like us to convert to z-scores. And it would seem like a daunting task if we had to rely on that formula that we just used for each one of these. I mean, that would kind of be a pain in the butt. But the good news is about this is that the standard deviation is 0.7 and 98.3 is the mean. So of course the mean is going to be in the middle. And it looks like each of these is just a single standard deviation away. So what that means for us is that these are going to be easy to label with regards to just thinking of them as z-scores. I mean, bottom line is that this is going to be 0. This, since it's one standard deviation away, it's going to have a z-score of 1. Since this is 2 standard deviations away, it's going to be a z-score of 2. This is going to be a standard deviation away to the left, which gives us a z-score of -1. This would be -2. Interestingly, I mean, they have this one right here, and they don't have it on the other side, but we're going to label it because it's there, and they asked us to label all these, so we just did. I think while we're at it, probably a good idea to also label this value in terms of its z-score and this value in terms of its z-score, and we already did that. This one right here, and when I say right here, I mean right here, is -1.86. And this one right here is 2.43, so I think that's going to be helpful. So we just satisfied 9C. Okay, D. What's the probability that a randomly selected person has a temperature between 97 and 100? Right, so in other words, what is the area of the shaded region? Because before they wanted us to shade the region between 97 and 100. Now they want to know the probability that, a randomly selected person will fall within this shaded region. And the way to do that is to use the table that kind of enables you to find z-scores and probabilities and relate them to each other. So we're going to do that right now. And before I start kind of breaking out those tables, it's important to realize that a lot of times when you use these tables that would relate z-scores to probabilities, a lot of these tables, whether it's in your textbook or even on Google, they're going to give you the area to the left of the z-score. In this case, this would be an example of the area to the left of a positive z-score. Sometimes these tables are going to give you the area to the left of a negative z-score. And The one thing that these two scenarios have in common, though, is that you're getting the area to the left of the z-score. That's important information for you to take into account, because what we're looking for is not the area to the left of 2.3, and we're not looking for the area to the left of negative 1.86. We're looking for the area between these numbers. So one thing you could do is find the area to the left of the larger z-score first. And I'll just draw that right now, where it's like, that would be like this area, with this being 2.43. We're going to find this area first. We'll call it A1. And then, separately, we're going to find the area to the left of the other z-score, which is negative 1.86, and we'll call that area 2. And basically, if we want to get the area in between these two guys, you could take the area of A1 and then literally subtract the area of A2. And can you see how that would essentially erase this little piece right there? And that would leave us with what we're looking for, which is the area between these numbers, right? So that's the strategy you're going to want to use for these kinds of problems. I'll just shade this back in for now. So our ultimate goal is to find the area of the first thing, and then we're going to subtract the area of the second thing, and that will give us our answer. So let's find the area of the first thing. So the area to the left of the z-score of 2.43. Well, the way that you find stuff like that is to use a table. And the table, really, in this case, got to be a table that features positive z-scores. And this is a good table right here. Here's a table that features positive z-scores, because we're going to try to find the area A1, which is the area to the left of a positive z-score. So let's see if we can look at it. The z-score is 2.43. So we're going to look for 2.4 over here, which is right here. Notice how this goes 0.00, 0.01, 0.02, 0.03, and so on. So we got 2.4, and then this is going to be the 0.00, this is going to be the 0.01, this is going to be the 0.02 across the top, and this is going to be the 0.03 across the top. So actually, this is the one that we want. That's 0.9925. 0.9925. So that is area 1, area sub 1. It's going to be 0.9925. And we're going to be subtracting whatever area sub 2 is, and that will be our answer, actually. So obviously, our next mission is to find area sub 2, which is this little area. Now, we got to be careful, because this z-score is negative 1.86, which is a negative z-score. And this doesn't feature negative z-scores, so we're going to need a new table. So I have here a table that features negative z-scores right here. So let's look at it. Before we do zoom into it, let's be clear. It's negative 1.86, so let's take a look. Negative 1.86. Well, we have negative 1.8 right here. Once again, across the top is 0, 0, 0.01, 0.02, 0.03, and so on. So this is negative 1.8. This is the 0, 0, 0, 1, 0, 2, 0, 3, 0, 4, 0, 5, 0, 6. So this is the one that we want. It's going to be 0.0314. 0.0314. That's area sub 2. So that is 0.0314. And when I finally subtract these, I end up getting 0.9611. So that's how you do that one. All right, looking at this one, the mean number of hours that American office workers spend on the computer is 3.1 hours per day. Standard deviation is 0.5 hours. Fill in the corresponding number of hours on the standard normal distribution graph below. Right. Okay, so it's kind of like working backwards from what we just did, where it's like they actually give you this standard normal distribution, and we have to retranslate these z-scores into the actual numbers. So that shouldn't be too hard. For example, the mean number is 3.1 hours, so that's going to be like this. 3.1 is the mean. Standard deviation is 0.5, so one standard deviation over is going to be to add 0.5 to 3.1. So this therefore is going to be 3.6. This one's going to be 4.1. This is going to be 4.6. And this one right here is going to be a standard deviation below 3.1. So that's going to be 2.6. This is going to be, let's see, 2.1. And this is going to be 1.6. Let's see. What's the random variable? Well, the random variable is the number of hours that American office workers spend on the computer. Find the probability that a randomly selected office worker will spend more than 4 hours on the computer. Right, so that's going to be this shaded region right here. You know, imagining that that's 4 hours. And the question is, if we're going to want to find this shaded region, I'll just tell you right now, it's always going to be a good idea to find the z-score associated with this and take it from there. Okay, so let's find the z-score first. This one's a little bit more complicated than the one that we just did, but we can still find the z-score first. So we're going to use this formula right here, where it's like x minus the mean all over the standard deviation. It so happens that we already have the x. We have the mean and we have the standard deviation. So it's just a matter of plugging those numbers in. X is 4, the mean is 3.1, and the standard deviation is 0.5. So after working that out, we would end up getting 1.8. So that is the z-score that corresponds with 4 hours. Okay. Now, some of you may have noticed that we have a little bit of an issue because we're trying to find the probability or the area of this shaded region, but we know that all those tables that we like to use always give us the shaded region, or most of the time they give us a shaded region that is to the left of a z-score. But here we are trying to find a shaded region to the right of the z-score. So we're going to have to be a little bit creative. The good news is that these bell curves are perfectly symmetrical. So what that means is the area over here could be matched over here. It could be replicated on this side, but we would just have to find the proper z-score here. And if we found this z-score, then we could just look up one of those tables and just take it from there. Now, the good news is we can easily understand what this z-score is, because this z-score is 1.8. So to avoid confusion, I'm just going to redraw the bell curve that we're dealing with. So we just found this z-score, 1.8, and it's really to find the area of this shaded region. But one thing we could do, because we have to rely on tables that only take into account areas to the left of a z-score, we could find this z-score right here, and then find this area. And this area is totally going to be the same as this area, as long as this z-score is a perfect reflection of this z-score. Well, that's easy. This z-score will be simply the negative version of this z-score. So in other words, all we have to do is use one of those tables, look up the z-score of negative 1.8, and we will get the area under this section of the curve. And since these bell curves are perfectly symmetrical, this area will be the exact same as this area. So once we find this area, we are literally done with this problem. Okay, that is the answer. So let's do that. Let's find that area right now. And in order to do so, we're going to bring back that table that depicted negative values, negative z-scores, I should say. So the negative z-score that we're looking for is negative 1.8. So we're going to look for negative 1.8. We have negative, let's see, negative 1.8 right there. And we have the 0, 0 column right next to it. So it's actually this, 0.0359, right there, 0.0359. So that is the answer, my friends. The area under this section right here is 0.0359, and we know due to the symmetry of the bell curve that this area right here is the exact same as this area, and therefore we just properly solved this question. The probability that a randomly selected office worker will spend more than 4 hours on the computer, well, that's here, and the probability is the area, so we're done. The graph below indicates the IQ scores of adults. Those scores are normally distributed with a mean of 100 and a standard deviation of 15. Right. The area of the shaded region is 0.8849. What IQ scores correspond to the shaded area? So what IQ scores correspond to the shaded area? In other words, really in other words, what is this IQ? Because once we find this IQ, we can answer their question by saying, like, you know, what IQ scores correspond with the shaded area? I don't know. All the IQs above this IQ. That's a nice, concise way of answering their question. All right. So our goal, you could say, is to just find this IQ. Now, I mean, you know, it looks like it's like, just under 85, but we can't really know for sure exactly what it is. So we got to figure out what it is. Now, my thought is, it'd be nice to at least find the z-score. Because if we found the z-score, then we could use this formula, right? To find the IQ, because the IQ would be x. And we could solve for x. If we had the z-score, we could just write it here. We could write the mean here, because we know the mean is 100. We could write the standard deviation here, because we know the standard deviation is 15. And then we could just solve for x, right? And then we'd be pretty much done. We have a little bit of a challenge. The challenge is that, yes, we want to find the z-score. We could use a table to find the z-score. In a sense, we'd be using the table just like before, but we'd be sort of going backwards. Instead of using the z-score to find the probability, we would be using the probability to find the z-score, because they give us the probability. But similar to the last problem, keep in mind the tables, at least the ones that I'm using here, only give you the area to the left of the z-score. This is another case where we're dealing with area that happens to be to the right of a z-score. So my thought is, what if we imagined that this curve, I'm going to make that a little nicer looking. What if we imagined that this curve was reflected so that the shaded region was here instead, and this was the z. And, you know, in the same way that this shaded region has an area of 0.8849, well, we could certainly conceive of an area to the left of a z-score having 0.8849, being 0.8849, right? So what if we found this z-score, and it would be a positive z-score, because this z-score is to the right of the mean. And once we found this z-score, all we would have to do is turn it to the negative version of itself, and we would get this. All right? So sometimes you have to kind of play in between. You have to take a scenario like this and temporarily flip it to this other side, get the positive z-score, and then that enables you to get, and then just turn it into the negative version of itself, and then you'll end up with this. So that's the game plan. My hope is that my student's teacher spent sufficient time talking about this trick of the trade, because it can get a little challenging. So what we're going to do now is we're going to find the z-score that corresponds with an area to the left of that z-score of 0.8849, and that therefore would have to be a table that takes into account positive z-scores, like this one. So looking at this table, we're actually going to look for 0.8849. We're actually going to hunt for it. So it's going to be around here, 0.8869, 0.8849. So I found it. It's kind of like playing Where's Waldo, for those of y'all who remember that. 0.8849 is right here. Now, what does that correspond with? Well, that corresponds with a z-score of 1.2 with this 0.00 there. So it's a z-score of 1.2. So we successfully found this z-score. So I'm actually going to just write it. It is 1.2. Now here's the thing though. As I said before, great, we found like the positive version of the z-score. But remember, this z-score over here is going to be negative. So actually the z-score that we're looking for is negative 1.2. So I'm going to write that here. That right there is the z-score. That is the star of the show. So let's take a look. Negative 1.2 is the z-score. So what that means is we can now find the IQ in question because we can now use this formula right here. Because we have our z, it's negative 1.2. So negative 1.2 equals x minus the mean, which is 100, all over the standard deviation. So solving for x, what we end up getting is 82. So that is the IQ. That is right here. And it's an IQ that happens to correspond with the z-score. 82 corresponds with the z-score of negative 1.2. We don't really need this negative symbol. So this IQ of 82 corresponds with the z-score of negative 1.2. So to answer their question, you might want to say something like, what IQ scores correspond to the shaded area? Well, all the IQs that are above the IQ of 82. Those are the IQs that correspond to that shaded area. So that's a crazy problem. Probably that's as complicated of a problem as my student is going to have to face on his test. Finally, IQ scores are normally distributed with a mean of 100 and a standard deviation of 15. Find the IQ score that separates the bottom 10% from the top 90. So this is a nice example of the kind of problem where you're going to want to draw the bell curve to give yourself an idea of what the heck is going on. Here's a bell curve. You've got a mean of 100. You know that the standard deviation is 15, so you're going to kind of keep that in mind. But we're looking for the IQ score that separates the bottom 10% from the top 90. So you know that that's going to be like here, right? And this is the bottom 10%. Whereas, this right here, big brackets, is the top 90. Now, I could already kind of tell that it's going to be helpful to think of these percentages as decimals, and you're going to see why in a moment. For now, I'm just going to call this 0.1, and I'm going to call this 0.9, and I'll draw a box around it to draw attention to it. So that's what we're dealing with, We want to find this IQ. Well, just like the last problem, if we had the z-score associated with this guy, then we could easily find the IQ, because think about it once again. We have this formula, this magic formula, where if we had the z-score, we could just put it here. We know that the mean is 100. We know that the standard deviation is 15 because they gave us that information. If we had these numbers, we could just put it in and then solve for x, and we'd be good to go, right? So once again, this is going to be a mission of finding the z-score first. In my opinion, this problem actually is easier than the last one, because what we could do now is just recognize that, all right, we know that the area here, this area, is 10% of the whole area, also known as 0.1. So this area is 0.1. There it is. So that's literally all we need to know. It's almost as though you can sort of ignore this 90% stuff, because all we need to know to find this z-score right here, all we need to know to find this z-score is this area to the left of the z-score, because then of course we could just use the table to find it. And that's what we're going to do. We're going to use the table that features negative z-scores, because we know that this z-score is negative. Why? Because it's to the left of the mean, right? So let's look at this table for an area or a probability of 0.1, and then we're going to find that z-score. That's what we're going to do right now. Looking for an area of 0.1. So that is, the area, pardon me, area of 0.1. Well, let's see, it's going to be around here, right? You got 0.985, and then it goes to 0.1003. So this is, I'm going to vote for this right here. Let's go with this, because that's really close to an area of 0.1. So we're going to find the z-score that corresponds with it. Well, it's going to be negative 1.2, and then to bring in the hundredths digit, it's 8. So this z-score is going to be negative 1.28. Negative 1.28. So this is no longer a mystery. The z-score is negative 1.28. That's the z-score that corresponds with this delineator right here, this IQ, that would separate the bottom 10% from the top 90%. And once again, why do we want the z-score? Because we could just plug it in right here. Negative 1.28 equals x minus the mean. We already know the mean. It's 100. All over the standard deviation, that's 15. So if we were to solve that so that we have x equals the number over here, x would end up becoming 80.8. So that, my friends, is the final answer to this one. In other words, the IQ of 80.8 is the IQ that would separate the bottom 10% from the top 90%. And that's how you do that one. So anyway, I hope you enjoyed it. Kind of a long one. kind of a dense video today, but for those of y'all taking statistics, obviously it's a lot of information. It's a completely different subspecies of math. It can get overwhelming. So I hope this video made at least some of the concepts clear for you. And thank you for watching, and I'll see you next time.